class is the second part of the lecture for respiratory system. So we left off on slide 70. So we're going to talk about breathing mechanics. Okay. So pulmonary ventilation, we have inspiration, which is breathing in of air, and expiration, which is breathing out of air. Okay. So we have some different pressures we're going to talk about. So let me write those on the board. So we have PATM. This is atmospheric pressure. So this is the pressure, I'll just put capital P for pressure, okay? So this is the pressure around us at all times, and this is what helps push air into our lungs when we breathe in. Now, we also need to overcome this atmospheric pressure, right? The pressure all around us when we breathe out. So we'll talk about how we do that, okay? So PATM is atmospheric pressure, and this is 760 millimeters mercury or 1 atmosphere. So millimeters mercury and atmospheres are both ways to measure pressure. Okay. Okay. So we are going to describe our respiratory pressures in relation to atmospheric pressure here. Okay. So another one that we have is intrapulmonary pressure. So that's P pul, intrapulmonary pressure. Okay. So this pressure here is the pressure in the alveoli of the lungs. So here I drew two bad drawings of the lungs. So here's our lungs normally. This one is showing a collapsed right lung, so we'll talk about that. But here's our intrapulmonary pressure, right? It's within the lungs because that's where you find the alveoli, okay? So it fluctuates when we breathe, right? The pressure is, of course, going to change when we breathe out, when we breathe in compared to when we breathe out, but it does eventually equalize with atmospheric pressure, okay? And then the last one we're going to talk about is intrapleural pressure, or PIP. Intrapleural. So I do that one here. It's within the pleural cavity, the pressure within the pleural cavity. Okay. So for intrapleural pressure, this also fluctuates as we breathe, of course, like any pressure within the lungs, okay? And it's usually 4 millimeters mercury less than the intrapulmonary pressure, okay? But if we have fluid that accumulates within the pleural cavity, then you would have a positive intrapleural pressure that develops and the lung would collapse. So that's what that picture there is showing. Okay, so we'll talk about that a little bit more in a minute, okay? So there's two inward forces that can promote this collapse of the lung. So one is the lung's natural tendency to recoil. So the lungs are elastic, meaning they can stretch, right, to fill with air, but then they want to assume their smallest size again, okay? But we have an outward force that helps to enlarge the lungs, which is the elasticity of the chest wall. So when I breathe in, my thorax comes out, right? My chest wall comes out, okay? So that helps to keep the lungs inflated along with a normal intrapleural cavity, okay, or pleural cavity, okay? And the amount of air that we keep in our lungs and the surfactant in our alveoli, okay, which keeps everything moistened so that the alveoli do not just collapse on themselves, okay? All right. So transpulmonary pressure is intrapulmonary pressure minus intrapleural pressure, okay? So this keeps the lungs open and keeps them from collapsing, okay? So the larger the transpulmonary pressure, the more open the lungs will be, okay? So if the intrapleural pressure equals the intrapulmonary, or if intrapleural equals atmospheric, then the lungs would collapse. Okay, so we need to keep a negative intrapleural pressure to keep the lungs expanded. Okay, so that's what this is showing here. So when our lungs are expanded here, intrapulmonary pressure is 0 and our intrapleural pressure is -4. So we want to keep this negative. We don't want it equal to atmospheric or intrapulmonary pressure. Okay. Okay. So now if our pleura is to fill with fluid, okay, so if there was like a cut here, so we had some sort of trauma where there was a cut within the parietal pleura, okay, now this pleura fills with fluid, maybe some air as well, okay, now our intrapleural pressure is equal to our intrapulmonary pressure. They're both 0, and all this fluid here is pressing on this right lung and it collapses. Okay, so I just wanted to explain all those pressures there. Okay, so we have different muscles for inhaling and exhaling. So for inhaling, we use our external intercostal, so that's between the ribs, the external muscles between the ribs, and the diaphragm, which is right underneath the lungs. Okay, so when we inhale, the diaphragm needs to push downward to make room for the lungs to expand. And then if we were to take a deep inhalation, so if I am to inhale all that I possibly can, the scalenes in sternocleidomastoid also come into play. So they'll also help to pull up the thorax, pull it up and out. Okay. When we exhale, we use the internal intercostals. And then if we were to forcibly push out a breath, right, we use some of our abdominal muscles as well. So we use our external obliques, our rectus abdominis, okay, and our internal obliques. Okay, so we use those abdomen muscles to help increase the pressure in our abdomen, okay, which decreases the volume and helps to push air out. Okay. Okay, now we're going to talk about one of the 3 gas laws. So the first one we're going to talk about is Boyle's law. So Boyle's law states that the volume of a gas varies inversely with its pressure. So kind of like what I just talked about with the muscles. When we increase volume, pressure decreases. Okay, so we don't want any pressure pushing out from our lungs when we're breathing in. So when we breathe in, volume of our lungs increases while the pressure inside the lungs decreases, okay, or inside the thorax. When we breathe out, we increase the pressure in the thorax, and that helps to push air out, and we decrease the volume within our lungs, okay? And this is the same for any gases within a system. If we were to increase the pressure and push down, if we have gases in a glass jar, there's my glass jar, there's gases in here. If we have something that pushes down, then the pressure is increasing when we push down, right? And the volume is decreasing. So first our gas took up this hole inside of the container, but if we increase the pressure, the volume decreases. So now in our cup, we increase the pressure, so we push down. So now the area of the cup is only down here, and now our volume of gas is less, okay? And gases always take up the shape of their container. So they take up as much room as possible. They spread out as much as they possibly can, okay? So this is one law that helps to govern our inhalation and exhalation, how we can breathe in and out, and how gas exchange occurs as well. So I talked about how we can breathe out because of Boyle's law, okay? Now let's talk about pulmonary ventilation, then we'll talk about the other 2 gas laws. So this one here is Boyle's law, okay? So, well, we talked about the muscles that are involved, okay? And we also already talked about the volume versus pressure when we breathe in, okay? So again, those accessory muscles of inspiration would be the scalenes, sternocleidomastoid, and the pectoralis minor as well. So those are accessory muscles involved in inspiration. The main muscles involved will be the intercostal. Okay, so the external intercostal and the diaphragm as well. Okay. Okay. Now let's talk about, there's 3 factors that influence how easily air passes and the amount of energy that's required for breathing or ventilation. Okay. So I'm running out of room here. So first is airway resistance. Okay, airway resistance. So this is friction that occurs within an airway. Okay. So if we have any sort of resistance to our gas flow, that is going to influence how easily air can pass, right? So this usually isn't an issue because remember we talked about the branching of the bronchial tree? It starts out, the trachea is the widest portion, then it gets smaller and smaller and smaller. So since those first parts of the airway are larger, the diameters are larger in the first part, okay, they get smaller and smaller, so there's an increase in the total cross-sectional area. So usually airway resistance isn't an issue for breathing, okay? So the resistance will usually occur in the like medium-sized bronchi, okay? But then it disappears by the time you get to the terminal bronchioles because that's where we have more diffusion moving gas or air. Okay. All right, then we have alveolar surface tension. So alveolar, hold this surface tension. Okay, so liquid molecules are going to be attracted to each other when we have gases and liquids communicating with each other, kind of near each other, interacting with each other, okay? So liquid molecules draw closer together to kind of stay with their own liquid molecules and stay away from those gas molecules that they're not super familiar with, okay? So water has a high surface tension and it coats the alveolar walls, okay, in a very thin film of water. Okay. If we just had this water, then the alveoli would collapse. But we have surfactant. So we talked about those type 2 alveolar cells. Those secrete surfactant. And it's a detergent-like material. So it's made up of lipids and proteins. Okay. So it helps to reduce the surface tension of water in the alveoli. So it prevents the alveoli from collapsing in on themselves. So if there's only water present, they would collapse in on themselves. Okay, and then finally we have lung compliance. Lung compliance. Okay, lung compliance is just the change that occurs. So how much stress, how much stretch the lung has. Okay, so if there was like scar tissue on the lung, for example, it wouldn't be able to stretch as much because scar tissue is very hard. Okay, it's not elastic at all. Okay, so but normally lung tissue is very distensible. It's a very spongy organ and it can expand greatly. Okay, so lung compliance, again, unless there's an issue like scar tissue has formed, okay, or there's not as much surfactant being produced in the alveoli, or for some reason the thoracic cage isn't expanding like it should. Those are the only three things that would affect or that would decrease lung compliance. Okay, now let's talk about lung volumes and capacities. So these are lung volumes and capacities. The volumes are on this side, including tidal volume, and then the capacities are on this side. So these capacities are, if you add some of these things together, you would get these capacities. The volumes are just the volumes, okay? You don't add anything together to get the volumes. They are what they are. Okay, so first let's talk about tidal volume. So this is the amount of air we can fit in our lungs just when we're at rest, breathing in and out. So we're sitting on the couch watching TV. This is how much we can breathe in and out in our breaths. Okay, so that's tidal volume. So I abbreviated it TV here. Okay, so that's about 500 milliliters. Okay, inspiratory reserve volume is up here. Okay, so if we were to take a normal breath in, like a short breath in like that, okay, how much now can I breathe in addition to that? So I take a normal breath in, now I breathe in as much as I possibly can, okay? That amount is my inspiratory reserve volume, okay? And it varies person to person, right? There's bigger people, smaller people. So it could be anywhere from 1900 to 3100 mil. You don't need to memorize the amounts. You could look at them on the chart in the PowerPoint, but I just want you to know what all of these volumes and capacities mean, okay? Then we have our expiratory reserve volume. This is kind of like inspiratory, but opposite, right? Expiratory is breathing out. So when we take a normal breath out, how much I could still forcibly push out a lot of air. So that's this volume here, expiratory reserve volume, okay? And then down here, this is residual volume, okay? So again, unless our lungs collapsed, they still have some volume of air within them, okay? We can never breathe out all of that air unless the lung were to collapse, then all the air would be pushed out, okay? So this here is the residual volume, the amount of air left in the lungs so that the lungs do not collapse. Okay. Okay, and now our lung capacities. Okay, so this here is inspiratory capacity. It's our tidal volume plus our inspiratory reserve volume. So if I were to take a normal breath out, how much I could forcibly inhale from there. Okay, so that's our inspiratory capacity. Functional residual capacity. That is if we were to take a normal breath out, how much we could forcibly push out plus what is left in the lungs. Okay. And then we have our vital capacity here. So this is our tidal volume plus our expiratory and inspiratory reserve volume. So this is how much, if I were to forcibly breathe in all that I could, how much I could push out without my lungs collapsing, or vice versa. If I were to push out all of the air I possibly can, how much I could now forcibly breathe in. Okay, that's my vital capacity. And then total lung capacity is how much air you could possibly fit in your lungs, including this residual volume. Okay, so do make sure you know all of those volumes and capacities and what you need to add together to get the capacities as well, and then what the volumes are describing. Okay. Okay, let's get back to our gas laws now. So we talked about Boyle's law. Now we're going to talk about Dalton's law of partial pressures. Okay, so Boyle's law. Now we have Dalton's law. Okay, so Dalton's law states that the total pressure exerted by a mixture of gases. So think about the air around us is a mixture of gases, right? We have nitrogen, oxygen, and very, very small amounts of other gases, okay? So again, total pressure exerted by a mixture of gases is equal to the sum of the pressures exerted by each gas. What the heck does that mean? It's actually pretty simple, okay? So Remember, our total atmospheric pressure is 760 millimeters mercury, okay? Now, nitrogen makes up 78.6, so nitrogen, 78.6% of air. Okay, so nitrogen is the most abundant gas in the air that we breathe on Earth. Okay, so to calculate how much pressure is being exerted on us in our atmosphere just from nitrogen, we can do 78.6% of 760. So you turn that to a decimal, 0.786 times 760 millimeters mercury. Okay. We did this out beforehand, so it equals 597 millimeters mercury. Okay, so this is the amount of pressure pushing on us just from nitrogen. We can do the same thing with oxygen. So oxygen makes up 20.9% of air. So we do 0.209 times 760 millimeters mercury, and what do we get? We get 159 millimeters mercury. 159. Exerted just from oxygen. Now, carbon dioxide is only a small percentage. It's only 0.04%. So you do okay, and we get only 0.3 millimeters mercury exerted on us from carbon dioxide. Okay, we'll come back to that. So this is Dalton's law. I'll actually write it up here. Okay, and then finally we have Henry's law. So let's actually move this here. Okay. Henry's law. Okay, so Henry's law states that for gas mixtures that are in contact with liquids, okay, so this happens inside the body, each gas will dissolve in the liquid in proportion to its partial pressure. So these are the partial pressures if we're talking about air specifically. Okay, but inside the body, things are going to differ a little bit because we don't have, we'll talk about it in a bit, okay? So it also states that at equilibrium, the partial pressures in both phases will be equal, and the amount of each gas dissolved will depend on the solubility. Okay, so carbon dioxide is 20 times more soluble in water than oxygen. Okay, and nitrogen is not very soluble at all. Okay, so an example of Henry's law is hyperbaric chamber. So this is a chamber that a person can be put in if they have some disease right, where you want to get more oxygen to the tissues. Okay, so maybe tissue is starting to die or something like that. You go into a hyperbaric chamber. Inside the hyperbaric chamber, the pressure is increased so that more oxygen is sent to your tissues. Okay, so gases only move down their pressure gradient, so from high pressure to lower pressure. Okay, so in blood, there is a higher pressure inside the blood. So that helps to cause carbon dioxide to move out of the blood and go into the alveoli, into the lungs to be expelled. Okay. But with oxygen, so there is a higher pressure outside of the blood. Okay, so in the alveoli, okay, there's going to be a higher pressure than in the blood for oxygen. So this helps oxygen to move out. Okay. Okay. So these gas laws help to explain how carbon dioxide gets sent into the lungs, and oxygen is able to move out and be sent to the tissues. Okay. Okay. So how are they transported? So the vast majority of oxygen is transported via hemoglobin, so it's bound to hemoglobin. Okay. So hemoglobin is made up of 4 polypeptide chains, so it's basically 4 proteins together, and each has an iron-containing heme group. Okay, so each hemoglobin molecule can carry 4 oxygens, 1 on each iron heme group. Okay, so most of that oxygen is transported via oxyhemoglobin, and only 1.5% of oxygen is dissolved within the plasma. Okay. But for carbon dioxide, most of it, about 70% of carbon dioxide, is transported as bicarbonate ions. 23% is carried by hemoglobin. So after it drops off some of the oxygen, there's space for the carbon dioxide to bind to the hemoglobin. And 7% is dissolved within the plasma. Okay, so now let's talk about this graph here. Okay. So this is a graph that shows the affinity of hemoglobin to bind to oxygen. So here on our y-axis we have percent saturation. So saturation is how much oxygen is bound to hemoglobin. And here we have our partial pressure of oxygen, okay, in millimeters mercury. Okay, I didn't write the numbers, but we'll talk about them as we go. Okay, so let's focus on the red sigmoidal curve here. Forget about the black and the blue, or the purple and the blue curve there. Okay, so let's just talk about the red. This is like normal circumstances. Okay, so about right here, this is the oxygenated blood in our systemic arteries. So they're going to be 98%. So let's use this color here. This is different from all of those. So right here, this is 98% saturated, okay? Which makes sense. We want our hemoglobin carrying as much oxygen as possible, and it only really gets up to around 98%, okay? Deoxygenated blood in the systemic veins, so somewhere around here, this is 75% saturated. So that right here is around 75%, okay? Now, if we subtract 75 from 98 here, how much oxygen was dropped off to the tissues? 23%, right? So we're not dropping off all of our oxygen. We're always keeping a store of oxygen on our hemoglobin, okay? So we only drop off about 23% of our oxygen at any given time, okay? Now, when we exercise, that's going to be maybe around here. Okay, we're at about 30% saturated only. So that means 68% of the oxygen is unloaded when we're exercising, right? When we're exercising, we need a lot more oxygen going to our tissues to help keep us going. So at that point, we can drop off a lot more oxygen, okay? Again, these two are kind of just like normal situation at rest, just hanging out, okay? But say we are lifting weights, right? Then we're only at 30% saturation because we've dropped off the majority of our oxygen to our tissues, okay? Because they needed it, okay? But if we have a decrease in pH, a high blood carbon dioxide level, a high temperature, or we'll talk about BPG later, then the curve moves to the right. Okay? This is known as the Bohr effect. Okay? So, what is the Bohr effect? So this is when the hemoglobin-oxygen bond weakens. So then we can drop off more. You see this is lower, so we'd have a lower saturation at in all of these situations, okay? So all those things cause the Bohr effect, okay? So again, lower pH, high blood carbon dioxide, high temperature will all move this curve to the right. We would have a lower percent saturation of oxygen, so more oxygen is sent to the tissues in those cases. However, if we had a higher pH, low blood carbon dioxide level, or low temperature, the curve would move to the left and we'd have a higher percent saturation. This is known as the Haldane effect. Okay, so we have a higher bonding with oxygen for hemoglobin. Okay, that causes the Haldane effect. Okay. So oxyhemoglobin, this is when hemoglobin and oxygen are bound to each other. It's known as oxyhemoglobin. So I just want to tell you some of those names. Reduced hemoglobin or deoxyhemoglobin is when hemoglobin has released its oxygen, okay, like to the tissues. Okay. And fully saturated means that the hemoglobin has 4 oxygen attached to it. Then you'd be fully saturated. Okay, so here basically all of our hemoglobin would be fully saturated. Okay, but somewhere like here, they'd probably be partially saturated. So maybe they'd be carrying 3 oxygen instead of 4. Okay. Okay. So what happens if we're at high altitude? So this is at normal altitude. At high altitude, our percent saturation only slightly decreases. So at high altitude, we're only at about here, 95%. Okay, so it doesn't actually decrease as much as some people may think. Okay, we still have pretty good saturation of oxygen, but it does decrease slightly. Okay, and at the tissue level, okay, remember at rest, our hemoglobin is 75% saturated at the tissue level. We only got rid of 23% of our oxygen. So this here again is at the tissue level. And again, if we're exercising, it decreases down to 30% saturated. Okay, so I just wanted to show you those 2 differences there. We already talked about the exercise one, but I wanted to talk about if you're at a high altitude. Okay. Okay. So BPG, this is biphosphoglyceric acid. This can also affect oxygen binding to hemoglobin. So this changes the structure of hemoglobin and it decreases hemoglobin's affinity for oxygen. Okay, so if BPG decreases, then the curve shifts to the left. Okay, decreases oxygen unloading. Okay, so oxygen will stay bound and it won't be unloaded, so it'll stay saturated. Okay. And BPG, what is BPG? It's produced by red blood cells. Okay, so when oxygen levels are low, BPG levels end up rising. Okay, so remember here, this is our partial pressure of oxygen. This has the biggest effect, right, on this curve. This is part of the graph here. Okay. 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 Now let me flip this over. Okay, now we're going to talk about exchange of gases at the alveoli and tissue level and exactly what happens there. Let me just make sure. Okay, good. Okay. So here we have our alveoli, and here we have a red blood cell, and then here we have our tissue, here we have a red blood cell. These are capillaries, right, that we'd have between, right? Red blood cell sends oxygen out of the capillary to the tissues, and then oxygen goes through the capillary into the red blood cell, and then vice versa with carbon dioxide. Okay, So what is going on here, right? Alveoli, so from the lungs, oxygen is sent through the capillary to the red blood cell, right? Then we get our oxygenated blood through the heart and then to the arterial system, to the tissues. And carbon dioxide is being sent through the capillary from the red blood cell to the alveoli. So red blood cell has picked up carbon dioxide from the tissues and is sending it to the alveoli to be expelled, to be breathed out, okay? So remember, the red blood cell, or the carbon dioxide, can be just found within the plasma, right? Dissolved in plasma. Or it could come bound to hemoglobin. So that's what this is showing here. We have carbon dioxide plus hemoglobin, it binds. Okay. Or it can come via bicarbonate. Okay. So here we have our oxygen leaving the alveoli, and oxygen now is going to bind to our hemoglobin, and now we have hydrogen ion left over because hydrogen was bound to hemoglobin before. So we have our hydrogen ion. It can bind with bicarbonate and then cause carbon dioxide and water, and then the carbon dioxide can be released. Okay. At the tissue level, kind of the opposite happens, right? So carbon dioxide is leaving and it's going to go into the red blood cell. Some of it's going to be dissolved in the plasma. Okay. Some of it is going to bind to hemoglobin. Okay, because now we're losing our oxygen. So now there's going to be some hemoglobin available to bind to. And then some of it is going to be carried as bicarbonate. Okay. So our carbon dioxide, when it comes from the tissue, is going to bind with water. Okay, that's going to become carbonic acid plus bicarbonate and then hydrogen ion. Okay, and this hydrogen ion helps the hemoglobin to release the oxygen to the tissues because it competes and binds to hemoglobin, and then oxygen is released. Okay. Now, both of these chemical reactions are catalyzed by the enzyme carbonic anhydrase. Okay, so it helps to catalyze both the forward and the reverse reaction here. Okay, so you should definitely note that. Okay, and then finally let's talk about hypoxia. So hypoxia is any sort of issue where you don't have enough oxygen being delivered to your tissues. So this can result in cyanosis. So when the lips start turning blue, that means that you are not getting enough oxygen to your tissues. So there are a few different types of hypoxias. Anemic hypoxia, this is where you don't have enough red blood cells or too little hemoglobin, or your hemoglobin is abnormal, so it doesn't bind to oxygen properly. Ischemic hypoxia, this is where you have blocked blood circulation. Of course, that would block oxygen from being delivered to the tissues. Histotoxic hypoxia, this is where the cells cannot use oxygen. So like when taking cyanide, for example, that is what happens. Hypoxemic hypoxia, this is where you have abnormal breathing, so you have some sort of pulmonary disease, or there's not enough oxygen in the air, so you can't breathe in enough oxygen. And then carbon monoxide poisoning, so carbon monoxide is it has a 200 times greater affinity for binding hemoglobin than oxygen does. So oxygen doesn't bind to hemoglobin if you're inhaling carbon monoxide. Carbon monoxide is binding instead. So then you wouldn't have oxygen being sent through the red blood cells to your tissues. Okay. And then finally aging. So aging, you'd have a decreased vital lung capacity, decreased blood oxygen level, decreased alveolar macrophage activity, and your respiratory cilia do not work as well. So elderly people are more susceptible to things like pneumonia, bronchitis, emphysema, and other breathing issues.